On the left is a flat, dull 3D diamond logo. On the right, a fiercely sparkling, photorealistic version of the exact same design. It is tempting to think the image on the right just has more digital spotlights pointed at it, or maybe a heavier glow effect applied in post-production, but that approach actually guarantees a cheap plastic result. The artists who build high-end visual effects rely instead on dynamic image-based lighting, or IBL. IBL is a technique that uses real-world photographic data to illuminate a digital scene, rather than relying on artificial light sources. Think of image-based lighting as placing your 3D logo wrapped inside a giant, invisible balloon. The inside of that balloon is lined with a 360-degree high dynamic range, or HDR, photograph. HDR maps store the true mathematical brightness of everything in a space, meaning the digital sun in that photograph is actually thousands of times brighter than a white piece of paper. Because diamonds and polished metals are essentially just collections of tiny mirrors, they need a complex, mathematically accurate world to reflect. Give them that world, and the human eye accepts them as real. To understand why that reflection matters so much, we have to look closer, a lot closer. If we zoom past the macroscopic level and dive down onto the surface of a polished gold ring, we find a rugged, mountainous terrain. Materials appearing perfectly smooth are actually microscopic hills and valleys. Straight light rays hitting this jagged landscape don't bounce cleanly, they ricochet in chaotic directions. A spectral microfacet distribution graph organizes the scattering into a predictable pattern, calculating the angles of these tiny mirrors. The math changes depending on the material. Metals are greedy. They absorb light and only reflect off the very top layer. But transmissive dielectrics, like diamonds, let the light inside to bounce around. Calculating the precise distribution of these microscopic hills is the exact mathematical difference between an object looking like cheap plastic and feeling like solid gold. Now, let's follow that light as it enters the interior structure of the diamond. White light is actually a bundle of different colors. Entering a diamond, the crystal structure slows and bends each color at different speeds. Governed by the Sellmeier equation, violet light travels slower and bends at a much sharper angle than red light. By calculating this exact mathematical splitting of light, we generate authentic fire inside the gemstone. We rely on the physics of the crystal itself, rather than pasting an amateur rainbow overlay. But all that internal bouncing creates a new problem. Light ricocheting between the gold setting and diamond creates messy visual noise called specular interreflection. To clean up this visual noise, elite visual effects pipelines track polarization, the specific direction that light waves vibrate as they travel through space. You know this from polarized sunglasses. By physically filtering out light vibrating horizontally, the lenses remove harsh, scattered glare, leaving a crisp, clear image. We do the exact same thing in our 3D software by deploying polarized radiance probes. These sensors mathematically detect light wave vibrations, allowing us to delete 30 bouncing interreflections. Analyzing polarization provides the visual clarity required to differentiate a confusing glowing blob from a sharp million-dollar piece of digital jewelry. When we pull back from the microscopic math, we can see how all these physical properties interact in the fully rendered luxury insignia. If we place the logo outdoors, the physics engine takes over. The microfacets and dispersion algorithms naturally catch the intense, overblown sunlight of a bright beach environment without clipping into pure white noise. If we move that exact same logo into a dark, atmospheric jazz club, the surface automatically catches the subtle, warm, low-light reflections. The logo reacts perfectly to these wildly different environments automatically. The artist doesn't need to manually tweak sliders or fake the lighting to match the background. This accomplishes our ultimate goal: absolute photometric consistency. Absolute photometric consistency is the state where a digital object reacts to light identically to its real-world counterpart across any possible environment. True high-end visual effects work is never about artistic guesswork or stacking glow plugins. It is an exercise in strictly enforcing the laws of radiometric physics. When we replicate light at the microscopic level, the viewer's brain accepts the image as real, and that technical accuracy translates directly into a sense of prestige.